In this video, we are going to look at the bond energy practice sheet. And so whenever we are doing a bond energy problem, we are looking at the energy used to break the bonds, so those would be the bonds of the reactants, all those bonds are going to be broken, minus the energy to form a chemical bond, and so that would be the product. So whenever we are looking at bond energy problems, instead of doing products minus reactants like we do for enthalpy of formation, we're actually doing the opposite. We're doing reactants minus products. Reactants minus products. So all we need to do for bond energy problems is add up all of the energies of the different chemical bonds holding together the reactants, and then add up the energy for the bonds holding together the products, and then subtract reactants minus products. And so we're going to do that for number one. So I like to circle all my different types of bonds in different colors. So my hydrogen-hydrogen bond, I have one of those on my reactant side, and I'm coming up to my table to find its value, 436 kilojoules per mole. Now we only have one of those bonds, so 436 kilojoules is my value. And then I also need to add in my other reactant, which is this chlorine-chlorine bond here. So chlorine-chlorine bond, I'm looking through my list. I have carbon-chlorine, here, chlorine-chlorine. This bond right here is my chlorine-chlorine bond. So I'm going to do this in a different color. I'm going to use blue this time. And this chlorine-chlorine bond has a bond energy of 242 kilojoules per mole, but I still only have one bond here, so 242 kilojoules. So these are my reactants. So I'm going to put this whole thing in parentheses. These are my reactants. And then I need to add up my products so I can subtract out my products. So looking over here, on my product side, I only have a single type of bond. I have a hydrogen-chlorine bond, but I have that bond 2 times. So our reactants, let's go ahead and put our negative sign between reactants minus, and we're going to put our products on the other side. So my products, I have a hydrogen-chlorine bond and another hydrogen-chlorine bond, so 2 times whatever the bond energy for a hydrogen-chlorine bond is. Hydrogen-chlorine is right here, second one on my list, and it has an energy of 431 kilojoules per mole. But we have 2 moles of that bond this time, so 2 times 431 kilojoules. And that will be the total energy of my products because I've used up all those types of bonds. So reactants minus products. And that will give me my overall bond energy. So first thing I'm going to do is I'm going to sum up my reactant values. 436 plus 242 gives me 678 kilojoules. Minus whatever the value for my products are. 2 times 431 gives me 862 kilojoules. So reactants minus products, doing 678 minus 862 gives me negative 184 kilojoules. So that is my enthalpy change for this first reaction, negative 184 kilojoules. On to the next problem. We have more types of bonds in this problem, so we're just going to add up all of those different bond values, and then add up the product bond values, and then do reactants minus products once again. So let's see. The first type of bond that I notice is this carbon-hydrogen bond, and I have 1 of those, 2 of those, 3 of those, 4 of those. Alright, so carbon-hydrogen bond, let's look at our list. We have 4 of those times whatever the value is for a carbon-hydrogen bond is 413 kilojoules. What other types of bonds do we have on the reactant side? Well, let's see. We have a carbon-carbon double bond. So we're going to add in one of that carbon-carbon double bond. Let's see, carbon-carbon double bond. See, it has a different value from a carbon-carbon triple bond, so you do have to be careful here. Carbon-carbon double bond is 614, and we only have that once, so 614 kilojoules. And then the last type of bond that we have on our reactant side is this fluorine-fluorine single bond. Let's see if we can find this on our list. Fluorine-fluorine single bond is 155 kilojoules. So those are all of our reactants put together. So all this stuff put together, these are our reactants. And then we need to subtract out the value of all of our bond energies for our products. So we'll do that on the other side. Alright, and now we moved a little closer so it's a little bit easier to see. So on the product side, we have a bunch of these carbon-hydrogen bonds again. So I'm going to use the same color. We have carbon-hydrogen bonds. Here, 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 and here. So we have 4 of those carbon-hydrogen bonds, and we already looked at that value. It's 413 kilojoules. And now on the other side we have a carbon-carbon bond still, but it's now a single bond. So instead of this double bond, we now have a single carbon-carbon bond. So I need to look up the value for a carbon-carbon single bond, which is right here, 348 kilojoules per mole. 348 kilojoules. Alright, and then the last type of bond that we have, that we haven't had any of these yet, we have a carbon-fluorine bond. And we have 2 of these types of bonds, one here and one there. So 2 times the value for a carbon-fluorine bond. So let's look at our list. Let's see, carbon-fluorine bond is 485 kilojoules. Alright, and that is all of the bonds on our product side. So here are our products. We're going to do reactants minus products to get our final answer. Now, to get our final answer, we'll need to enter these values into our calculator. But first, we can notice that we have some of the same values on each side. So instead of entering those into our calculator, we can just cancel them out. This 4 times 413 kilojoules, we have that on both sides of the equation. So instead of entering that in, we're just going to cancel them out. 4 times 413 minus 4 times 413 is going to be 0, so we don't need to do those values. So all that's left is 614 plus 155 on our reactant side, and then the 348 plus 2 times 485 on our product side. So we just simplified the math that we needed to do just a little bit here. So let's see, 614 plus 155, that gives me 769 kilojoules on our reactant side, minus 348 plus 2 times 485, 1318 kilojoules on our product side. So reactants minus products, let's do 769 minus 1318, gives us a final answer of negative 549 kilojoules, which is our final answer. Alright, for number 3, we're going to use a slightly different strategy to solve this problem. For this problem, we're going to go through and we're going to look at the bond types on each side first to see if we can use that cancellation strategy like we did in the previous problem. So I see carbon-hydrogen bonds on my reactant side. I see... And let's count how many of those we have, and we'll circle these in pink. So carbon-hydrogen, I have 1, 2, 3, let's see, 4, 5, 6. So I have 6 of these carbon-hydrogen bonds. A different type of bond that we have is a carbon-oxygen bond. Now let's see how many of those we have. We have 1, 2 of these types of bonds. And then a third type of bond that we have is an oxygen-hydrogen bond, an OH bond, OH, and we have 1, 2 of those. So by doing this, I can make sure that I count every single bond on each side of my problem, whereas if I wasn't circling them as I went, I might accidentally forget a type of bond. So let's do the same thing on the other side, and if we have the same types of bonds, we will try and use the same color to circle them. So first, let's see, do we have any carbon-hydrogen bonds on the other side? And we do. We have at least one carbon-hydrogen bond. So let's count those now. Carbon-hydrogen 1, 2, 3, 4, 5, 6. Okay, so we have 6 carbon-hydrogen bonds. There's none over here. All right, next let's see if we have carbon-oxygen bonds. Let's see, carbon-oxygen, we have at least 1. So let's go ahead and write it down. We have 1, 2 carbon-oxygen bonds. Let's see, do we have anything else? No, just 2. Okay, and then do we have any oxygen-hydrogen bonds on our product side? Well, we don't have any here or here. We already used all these bonds up. We do have an oxygen-hydrogen bond here, though. And we, in fact, have 1, and then another one, 2 oxygen-hydrogen bonds. Okay, so now we've done this. So before we go about finding all the values for bond energies like we've been doing, let's look and see which bonds appear on both sides. Well, we have carbon-hydrogen on the reactant side and carbon-hydrogen on the product side, and we actually have 6 on both sides, so these are going to cancel each other out. If we take the value for carbon-hydrogen, let's see, is 413, 6 times 413, and then we have 6 times 413 on the other side as well. So we don't even need to do that math. We know 6 times 413 is going to cancel out 6 times 413 on the other side. So let's cross those out. My pen didn't work very well that time. Put an X through that, X through that. Okay, same thing, let's see with carbon-oxygen. We have 2 on the reactants and 2 on the product side. So that carbon-oxygen, those 358 kilojoule bonds times 358, well 2 times 358 and 2 times 358 are going to be the same value on both sides. So these also cancel out. So we don't need to do that math either. Those are going to cancel each other out. Then last but not least, we have oxygen-hydrogen. We have 2 on the reactant side and 2 on the product side. So even before we look up here for its value for 463, we know that 2 times 463 is going to cancel out 2 times 463. So these cancel out as well. So our enthalpy change for this reaction is 0 kilojoules, because we have the same types of bonds on both sides of our reaction. I'm going to move that up so you can see a little better. We have the same types of bonds on both sides, so our overall enthalpy change is 0 kilojoules. There is no enthalpy change for this reaction as estimated by bond energy. Alright, so this next problem is a little bit different because we do not have Lewis structures drawn for us. So before we are able to look at our values for each bond, we have to actually draw what the Lewis structure looks like so we know what types of bonds we have. So this is why we did a Lewis structure review, because we do need to be able to draw Lewis structures. And so first, before we can do that, we need a periodic table. So let's make sure you have a periodic table handy so we know how many valence electrons each substance has. Hydrogen has 1 valence electron, so each hydrogen atom has 1, and there are 2 hydrogen atoms here, so this Lewis structure can use a total of 2 electrons, 2 E minuses. So we draw our atoms, our 2 hydrogens, draw our skeletal structure, connect those 2 H's, and wow, we already used both our electrons because we know a bond includes 2 electrons in it. So here is our Lewis structure for H2. We don't have any remaining electrons to distribute. And we only have 1 H2 molecule here, so this is our Lewis structure. We are good to go here. Next we have CO2, so a little bit more complicated. Let's see, carbon has 4 valence electrons. Plus 2 oxygen atoms. Oxygen has 6 valence electrons, so 2 times 6 would be 12. So we get a total of 16 electrons here. Now, our atom that's going to go in the middle is the one that's furthest to the left on the periodic table, so that would be carbon. And we'll connect our two oxygen atoms to our carbon atom, drawing our skeletal structure. So drawing that skeletal structure, use 2 4 electrons, so -4, so we have 12 left to use, and we distribute those to the outer atoms first. So let me start doing that. If I distribute 2 4 6 to each oxygen, 2 4 6, that uses up all my electrons and leaves carbon unhappy. So I know that I'm going to have to introduce multiple bonds here. Instead of giving each oxygen 6 electrons, let's try giving them 4. And then try putting a double bond in here. So now I've used 2, 4, 6, 8, 10, 12, 14 electrons. Carbon's still unhappy, so let me see, add another double bond here. So now I have 2, 4, 6, 8 for my oxygen, 2, 4, 6, 8 for my carbon, and 2, 4, 6, 8 for my oxygen. So that's my correct Lewis structure. And there's no coefficient, so I only have one of the carbon dioxide as well. So there are my two reactants. Now I need to draw my products. Water's Lewis structure is a very common one. You may already know how to draw it without looking up its electrons, but if we do, each hydrogen has 1 valence electron, so 2 times 1 gives me 2, plus oxygen has 6 valence electrons, so plus 6, that's 8 total. Oxygen, it's going to go in the middle because hydrogen is never a central atom, so oxygen goes in the middle. And we put our hydrogens surrounding it. And we used 4 of those 8 electrons. We have 4 left over. The only atom that's unhappy is oxygen, because hydrogen only wants a duet of electrons instead of an octet. So hydrogen has 2 and hydrogen has 2. Oxygen has 2, 4. So it wants those other 4 electrons. So we're going to give those pairs of electrons to oxygen. So now oxygen has 2, 4, 6, 8 electrons, and each hydrogen has 2. Alright, moving on to carbon dioxide. Carbon has 4 valence electrons, plus oxygen that has 6, so that's a total of 10. There's no central atom here because it's only 2 atoms. So carbon, bond to oxygen. We use 2 of those electrons, we have 8 left. Each of these atoms wants an octet, so they each need 6 more electrons. I know that I don't have 12 more electrons, so I'm going to try doing a double bond. Now they each have 4 electrons, so they would want 4 more each to be happy. So let's see, I use 2, 4 electrons. So now I have 6 electrons left. Let's see, so 2, 4, 6, 8, 10, 12. That doesn't work. So I know I'm going to have to introduce another bond, use another 2 electrons. Now I have 4 left. Carbon has 2, 4, 6, so does oxygens. They each only want 2 more, so these 4 electrons can make them happy. So let's put 2 on each person, and then we've used up our remaining 4 electrons. And we only have 1 of each thing here. So now that we have our Lewis structures drawn, let's add up the reactants and the products and do reactants minus products. Let's see here. So let's look at each type of bond. We have a hydrogen-hydrogen bond on our reactant side. We have a carbon-oxygen double bond on our reactant side. We have 2 of those. And we have 1 of our hydrogen-hydrogen bond. Then on our product side, we have some new types of bonds. We have an oxygen-hydrogen single bond, and we have 1, 2 of those. And then we have a carbon-oxygen triple bond, and we have just 1 of those. So let's go ahead and multiply by all those values. None of the bonds exist on both sides of the equation, so we do have to do all of our math. We can't cancel anything out. So let's see, hydrogen-hydrogen single bond is 436 kilojoules. Carbon-oxygen double bond, let's see, let's look at our list. Carbon-oxygen double bond is 799 kilojoules. An oxygen-hydrogen single bond is 463 kilojoules. And a carbon-oxygen triple bond, not the double, but the triple bond, is 1072 kilojoules. Let's do some math. 1 times 436 is 436. 2 times 799, so 800 times 2, 1600 is 1598. And then we'll add these reactants up, and we'll add the products up, and do reactants minus products. 2 times 463, I'm going to pull out my calculator for. 2 times 463 gives me 926. And then 1 times 1072 gives me 1072. So let's add these values up. 926 plus 1072 gives me 1998. That's my products. Now I need to do 436 plus 1598 for my reactants. 2034. Now reactants minus products, make that negative sign really nice and big. 2034 minus 1998. It's going to give me a positive number, positive 36 kilojoules. So that is my answer. Positive 36 kilojoules is my enthalpy change for this reaction. Oh, move that up just a little bit so you can see that final answer, positive 36 kilojoules. So this may seem like a lot of work, and you're right, it is a good bit of work to draw out the structures and to add up all these values and then subtract. But the process itself is actually fairly simple, because the only math we're doing here is adding and subtracting. So as long as you can draw your Lewis structures correctly, and then pick out your bond types, as long as you're careful doing this, there's no reason that this should be particularly difficult. It just does require that you stay organized. And so that's the biggest thing I'm showing you here, is how to stay organized whilst doing this method. Because if you don't stay organized, it is easy to miss a bond, and then your answer ends up wrong just because you missed one single bond. So be careful, stay organized, and you'll be just fine.